So we talked about the notion of standard deviation. Now let's go back to talking about distributions. Remember, we're talking about the distribution for a particular variable. And let's look at this picture here. Histogram of vocabulary scores of all 7th grade students in Gary, Indiana. The smooth curve shows the overall shape of the distribution. So the variable here is what? It's a grade equivalent vocabulary score. So again, it goes from 2 to about 12. And we can see that there's sort of like a peak around about 7. And so the red line there is just an attempt to show the shape of this distribution. So for example here, well, let's go down here. So here, again, we have the same picture. So we said that the variable here is the grade equivalent vocabulary score. So it's a score for the students. And it ranges between 2 and maybe 12 or something like that. And so some of the students got scores around 2, some got scores around 4, some got scores around 8, and so on. So we can ask how many students or what percent got scores around 2, and that's represented by the height at 2. We can ask how many got scores around, what, I guess that's 2, what would that be? 2 to 2.5, 2 to 2.5, then 2.5 to 3, and 3 to 3.5, and 3.5 to 4. So we could ask, say, how many got between 2 and 2.5, and that would be the height of the first bar, and how many got between 2 and 3, and that would be the height of the first 2 bars. Okay? So we could also ask up here, they ask the height, I'm sorry, the shaded bars represent the scores that are less than or equal to 6, right? And then in figure 3.2b, the proportion of the scores less than or equal to 6 from the density curve is 0.293. Now, without going into a lot of details, this curve, or sorry, these bars represent the percentages. And so the height or the area under that curve will tell you the percent. So if you want to know approximately what the percent of students that got scores less than or equal to 6.0, that's going to be approximately the shaded area in figure 3.2b. Okay, maybe not exactly because it's the actually the bars, but it's approximately the area under the shaded, under the curve. So we talk about what's called a density curve. This is an example of a density curve. So what is a density curve? It's a curve that is always on or above the horizontal axis. So that's true of this red curve here. And it has an area exactly 1 underneath it. So the area, remember, it represents the percent. So the total area under the curve should be 1. Okay, so that's what we mean by a density curve. So, of course, there are many ways to draw a curve that's always above the x-axis, the horizontal axis, and has an area of 1 underneath it. It doesn't have to look like this curve. So any such curve will be called a density curve, and this is an example of it, and this one has a particular name. It's called the normal curve. So the density curve in figure 3.1 and 3.2 is a normal curve. Density curves, like distributions, come in many shapes. 3.3 shows 2 density curves. A symmetric. Okay, let's look at that. So here are 2 more. density curves. They're density curves if they are always above the horizontal axis and their area underneath them is 1. So we don't really know what the area underneath it is, so we can say it could be 1. So we have two of them here. The one on the left is symmetric about the center line there. On the other hand, the one on the right is not symmetric about either of those drawn in vertical lines. So okay, so when you have a symmetric curve, the mean and the median are going to be the same thing, whereas on the curve on the right, which is skewed to the right, the mean will be greater than the median. And this figure here is showing you where, if you think of a curve like being put on a seesaw, the place where it balances is going to be the mean of that distribution. So like we said before, if you have a symmetric curve, then it's going to balance at the center, and that means that the mean will be at the center, right in the middle, I guess I can say. And the median will be different than that, possibly, depending on the shape of the curve. Here's another pardon me, density curve. Here you can clearly see that the area is 1 because the base is 1 and the height is 1, so the area is 1. So one particularly important class of density curves has already appeared. These density curves are symmetric, single-peaked, and bell-shaped. They are called normal curves, and they describe normal distributions. Normal distributions play a large role in statistics, but they are rather special and not at all normal in the sense of being average or natural. Okay, anyway, let's see. The exact here. We capitalize normal to remind you that these curves are special. All normal distributions have the same overall shape. The exact density curve for a particular normal distribution is described by giving its mean and its standard deviation. Now remember, the curve, you can sort of think of it as representing a bunch of data, and the data will have a mean. So we can talk about the mean for that curve. And the data will have a standard deviation, so we can talk about the standard deviation for that curve. The mean is located at the center of the symmetric curves and is the same as the median. Changing mu without changing sigma moves the normal curve along the horizontal axis without changing its spread. On the other hand, the standard deviation controls the spread. Okay, so here's an important picture. Two normal curves showing the mean mu and the standard deviation sigma. So if these are both normal, or if these are both in fact just density curves, the area must be 1 underneath the curve, but they're both apparently centered at mu at the same place. So, but they're different, and we say the spread of the one on the left is greater than the spread of the one on the right. Okay, let's stop here.